Hello, everyone, and welcome to another Into the Terminal. Today, you'll just be hearing from me. But don't worry, Nate is here. He's just producering today because he is feeling a little bit under the weather. So today we're going to talk about application. Oh, there he is. Application profiling a bit. And we're going to focus on a couple of tools. So why don't we go ahead and jump into the terminal. And the genesis for this episode was because I was watching another YouTuber and they were talking about the time command as a really handy command. And I'm like, oh yeah, time, that's cool. So if you've not seen it before, time will tell you how long a thing takes. Right, so down here at the bottom, it's basically a wrapper for your command, and it tells you how much actual human time has passed. That's real time. It tells you how much user space time in compute time that your thing took, and system time, which is the amount of compute time used for systemy things that you end up with this command. So that ls user bin took a total amount of time of 0.27 seconds. And you can see that most of that time was spent doing system activities, right? Which kind of makes sense because if you're doing an ls, you have to do some disk IO. You have to look at things like the inodes to figure out that like Z-solim there that's bright blue. That's a symbolic link. So you had to access the file pointer to figure out what type of file it was in order to highlight it correctly, right? So there's and it output all the stuff to the terminal window, right? So there's like a bunch of stuff like that that's happening during this run. And that's cool. And time is a great bash keyword, right? So this is actually implemented in the bash shell. And it gives you this very quick synopsis of how long your thing took and a little bit of information on what it was doing. But that got me thinking, because I think there's a lot more here in what is this thing doing. So for that, we have a tool called Strace. And Strace will report back to you all of the system calls that an application makes during the course of its execution. It is also a wrapper. So just like we preceded our ls command with time, we're going to precede our ls command with strace. And then that's what's going to allow it to profile that application. So let's do that. All right, so we have this strace ls user bin. We're going to run the ls user bin. We'll actually see the output from it, but we'll also get all of the system tracing, the system call tracing out of it too. And it's going to look really disgustingly awful. So I will warn you in advance because you're going to get to see all the stuff that's actually happening during this. And in order to get the strace command, I had to install the strace RPM. All right, so before we started the episode, I did a DNF install of strace, and that's what gave me this command. The other thing I installed before the show is the man-pages RPM, and you'll see why I did that in just a second. All right, so here is our ls, but straced. Oh, and we've exceeded our scroll back. So let me do that again, but pipe it to less. All right, so here's the actual output that we get, right? All this list of files, that's what we're seeing in the output of our ls. And then once the output of the command that you're running with strace has been generated, then you'll actually get to see the strace itself. So let's wait a little bit further. Nope, let's try it again. And rather than, let's try one more time. All right. So this is what scrolled by really quickly that very first time that I said it was going to be really disgustingly awful to look at, right? And these are all the system calls. And then here's the actual output from our command. And then down at the end, right, we get a couple more system calls like close and exit group, right? All right, so what we're seeing is all of the system calls that have been made by this ls command, starting with the exec of the user bin ls binary, right? And then we have to map some memory, and we get some, we access this shared object library, and we open this shared object library, and we get a file status of something hidden in that dot, dot, dot there. And then we allocate some more memory, and then we close the file we opened, right? So this is just the beginning of like getting it set up, right? You can see here, we're doing another shared library and storing it. We're doing another shared library and storing it. We're doing another shared library and storing it. And each time we're kind of allocating some memory to store the shared library that that this application is going to use. And then a little bit further down, we get into some other calls like mprotect, which is allocating protected libraries, or I'm sorry, protected memory rather, and how much it should allocate and other things. All right, so this is where that installing of the man pages RPM, the man dash pages RPM becomes handy. Because as you're reading this scroll of stuff, I was telling you what all these different system calls do, but what if you didn't know? So like what is mmap, for example? So if we do a man on mmap, it is a C library that will do the following things, right? This is the system call, and it tells you a description about what this thing does. So as you're going through your strace, you can look up all these different system calls and then get really detailed information on what they do and how they work. And if you're really diligent, you could do stuff like figure out the arguments that are being passed that you also see in the strace output. But that's probably more effort than is usually worthwhile. Because strace is great for answering questions. And so running strace and getting the giant pile of stuff that it does is interesting. It can be really handy when attaching to running processes, and I'll show you an example of that in a bit. But just like running commands with strace attached to it is probably not super interesting, right? Unless you're trying to introspect on what is the process of things that this does. Strace is really interesting for doing more granular profile, or sorry, more aggregate profiling, but also trying to troubleshoot something to figure out what something's doing while you're having problems with it. So let me show you a couple other options for strace and how we can use it. All right, so looking through that giant scroll back of ls, interesting, I guess. But what if we instead strace -c? So the -c says, don't show me the giant scroll back of system calls. Instead, count the system calls and then give me some additional data about them. Right. So up above, here's all my output of my ls. And then down at the end, there's the strace -c. So it gives you an amount of time that each one of these system calls took. So notice that the percent time column, it all adds up to 100%, right? So it's going through and it's showing you that 64% of the time that we're waiting for this thing to run and be finished, 64% of the time, we're waiting for write system calls. And 10% of the time, we're waiting for exec VE system calls. And 8% of the time, we were waiting for mmap system calls. And then the other interesting thing that's in this count is right here. This is how many times this system call was made during the strace capture. So 588 times the ls command called the write system call. And one time it called the exec VE system call. And 36 times it called the mmap system call. And so what you can do with this breakdown of data is, for one, we notice that write system calls don't take very long. In fact, there's another column that says usecs per call. So that's how many microseconds on average each of the calls to this system call took. So writes take 6 microseconds, whereas execve, there was only one call and it took 611 microseconds to complete. So you start to get a sense of not only what does this application that you're profiling do in terms of like what system calls is it making, but you also get some sense of how much time and how efficient these system calls are. So down at the bottom, like who knew that to run an ls was 747 system calls, right? And that the on average microseconds per system call was 8. And then the overall amount of seconds that it took was 0.006 seconds roughly to run this command. All right. So that's pretty interesting. But we're looking at a command that doesn't run very long and also doesn't do a lot of stuff. So how about we take a look at a different, much longer running command. All right. So we're going to strace this find command. And we're looking for a file named floof, which I don't think exists on this machine, so it shouldn't output anything. And then I'm taking all of the error messages that could be generated by the find command, and I'm just chucking them in dev null, which is a special character device that accepts all input and doesn't actually store it anywhere. All right, so let's see what we get out of this guy. And producer Nate, I'm sure, is shaking his fist at me because because I'm going off script. Oh, and let's add in another option. Hold on. I know the problem. By default, the strace output also goes to standard error. So how would we just put this into a file? We'll just let it come to the terminal. So by default, strace prints all of its output to standard error. So by me redirecting the errors from the find command, it's actually redirecting the errors from strace and sending it to dev null, which is why it was returning no output. So a little bit of better quoting on the command line probably would help me out there. All right, so here's what this find command did. It spent almost 25% of its time doing F controls, right? File controls. It spent 21% of its time doing closes on files. It spent 20% of its time doing get dent 64, right? Which is get directory entries, but the 64-bit version. And it spent 11% of its time doing file stats. It spent 11% of its time doing opens. And here's why. Find is looking for these files and it's having to do all of this disk IO, right? And it's having to do things like check permissions on directories and all kinds of other stuff. It's combing over the directory tree. And again, like if we didn't know what a F control is, we could just do a man on fcntl, right? So F control manipulates a file descriptor, right? So find, trying to find all the files on your machine, is accessing file descriptors, which are things like inodes and have other properties and other things on the file. Close is closing files, and I said get dents 64 is directory entries, but we could verify that with get dents 64, right? So get directory entries, which is also an important thing for find to do because it needs to know what files are within a directory so that it knows if any of those are directories themselves, so it can recursively continue looking on the file system for the files that match the criteria you provided. All right. So this is like basic application profiling, right? So you can use Strace, you can wrap your commands with it. You can kind of see kind of what's happening on the system behind the scenes. I like using -C because it gives me some timing information as well as the overall number of calls and some time each individual call makes on average, so that I can kind of figure out what's happening when I'm doing this thing. But the other really handy thing for Strace is attaching it to running programs. So like running it as a wrapper is neat when you are having a problem with the command that you're running. But what if it's a service that's running? You don't usually interact with services on the command line, right? They're like daemons running in memory, and they're just like out there, started up by systemd. How do you figure out what's happening there? All right, so this is the other super powerful thing with Strace. All right, so before the episode started, I started up all these different Apache. Well, I started up the Apache web server, and it started up these worker daemons. And so the first one that like attaches to the privileged ports, that one is owned by root. And then there's these 4 worker daemons that are all owned by Apache. So how about we are interested in knowing when I make a request from one of these daemons, which one is it going to? Or is it like going to each one round robin, right? How does it actually work, right? So I'm going to make a little bit of extra room for myself. All right, so I'm just going to split using tmux so that I have 2 entries on my screen here. And I'm again going to look for my Apaches. There we go. And I'm going to come up here and I'm going to attach an strace to one of these worker daemons, right? So I'm going to strace -p because I'm going to give it a process ID to attach to. And I'm going to attach to 253230, the first one in the list of worker daemons, right? This one right here. All right, so here we go. This process is sitting there in accept state. So it's basically like accepting connections, right? So if I'm down here and I do a curl, oh, wait, hang on. Let me see what my IP address is. Curl 10.0.2.2. It's not doing anything on the top. And let me, because maybe it's serving them round robin, right? So if I hit it a few times, if it was serving things round robin, it should get around to this daemon, right? So let's just do it a few times. Nope, I made more than 4 requests. So if it was serving requests round robin across all the workers, I should have seen something out of this guy. And let me go back up to the top and Control C. All right, so let's attach to another one. And actually, I'm going to add one more option this time. FP. So F says follow forks. So if this process forks another process, strace will attach to that process too. So let's go to 253.231. Ooh, this looks more promising. So let's go back down here and do my curls. Oh, and there it's doing some stuff, right? You see some things in the you see some changes in the strace output. All right, so let's go to the next one. So it's 232. All right, let's see if he's doing anything. So as I'm making requests, he's servicing some things. All right, let's Control C and go to the fourth one. This one is 253276. Yeah, it doesn't look like he's serving any connections. So it looks like when I'm banging away with connections, it's only the 2 of the 4 worker daemons that are actually receiving them. And that's because Apache, the root-owned daemon, helps you spell grep correctly. This guy right here, that's weird. The root-owned daemon is taking care of kind of directing which of the worker daemons is getting the incoming connection. And it knows when it's handed off the connection to somebody and when it's available again. And so if I'm requesting very fast, instead of only going to one daemon, it ends up doing some of the connections on another daemon. If I am going slower, and the first daemon would be able to handle all of the requests, it would have never fallen over onto that second worker thread. So you can use Strace to connect to something and see what it's doing and how it's working. You can see that it's sitting here doing a pselect6. I actually don't know what pselect6 system call is. So let's do a man on pselect6. So this is synchronous IO multiplexing. All right, so this is how the main daemon is actually figuring out who to send stuff to, is through pselect6. So yeah, that's, you can answer questions. So if you're having things like daemon seems slow, right? You can connect with Strace and kind of see what system calls it's making. Also, we could see when we connected to one of those daemons that pselect6, like that's what it was doing a lot of its stuff, right? That's what it's spending a lot of its time doing. And so if that's your daemon is slow and that's the thing it's spending all its time on, you can start introspecting on what is that system call? What is that system call responsible for, in order to figure out what this thing is spending its time doing if it's behaving weirdly, right? One other thing I wanted to show us is you can also do the count with Strace on an attached PID. So if you don't want to just look at the scroll of system calls, and instead you like that aggregate table that kind of reports on what it's doing during the observation period and how long each thing took, you can actually use Strace -F, follow forks, C, produce for me the count, P, I'm going to attach you to a running process, and then here's the process ID I want you to attach to. And Strace is running here, and when I hit Control C, that's what's going to disconnect the Strace from the process and then generate the table. So this process, while Strace was connected to it, did 387 calls to pselect6, right? Because nobody was actually making web content requests from it. So this is a really handy way to kind of see what's happening inside of a running process if it's behaving weirdly or oddly. All right. Cool. So that's a lot on Strace. Let me look back at the chat to see if we've got anything interesting. Oh, I see Nate chiding me for going off script, because that's always dangerous. And nothing really else in chat. Some talks about Toyota Hiluxes, which is always a good topic for conversation. All right, so let's talk about another profiling tool. So in addition to Strace, there's also a program called Ltrace. And to get it, I had to install the Ltrace RPM. All right, so just like I installed the Strace RPM to get Strace, I installed the Ltrace RPM to get Ltrace. And let me see if I can count that. All right. So Ltrace has much the same syntax as Strace. So it works as a command wrapper. And then it reports to you the running tally of what this thing is really doing. But unlike Strace, which traces system calls, Ltrace traces library calls. So all those shared libraries that your applications use, your applications will make library function calls to them. And that's what Ltrace is showing you. Ltrace is showing you the library function calls for the shared object libraries that your application is making calls to. So we could watch it flow through, and we can kind of see some of the arguments that are being passed to the shared library function calls. Or just like Strace, you can use -c to give you this nice count. So you get a breakdown of how much time each of these and how many of these your application was making. And then average microseconds per call. So this is also handy, but I find it more handy when I'm troubleshooting my own applications, right? So like I've written a thing and it's not behaving properly, and I can look at what my application is doing. And because I'm a programmer that has written this application, I'm more familiar with what library calls and what activities I expect the application to do. And so if I'm having problems and I need to get information on like what's taking so long, or why is air no location taking 11,000 calls, like I can better introspect on my application to figure out what I may need to go in there and look at specifically if I'm having problems with my application. All right, and then the last couple things, because we're getting close to our normally allotted 30 minutes. The last thing I wanted to spend a little bit of time on is BPF tools. So in the kernel, there is a sandboxed virtual machine that is the eBPF virtual machine. So because it shares memory with the kernel, it's able to get real-time data from the executing kernel on your machine. And there's a whole bunch of tools that we've produced called the BCC Tools that will access those eBPF data calls to collect data and then format it so that you can easily read it, right? I installed the BCC Tools RPM, which put a whole bunch of tools in user share BCC Tools. And notice that this directory is not in your path environment variable, right? So if I just tried to run file slower, right, doesn't work because user share BCC Tools isn't in my path of executables. So when I work with the BCC Tools, I can either add it to my path environment variable, or I can just go into this directory and run them, or I can provide fully qualified file names to run them. So one of the ones I like doing is BioTop. And there are a few tools called something top in the BCC Tools. And this is doing block IO top, right? So we can see what processes are doing block IO requests. And then also gives me a little bit of data on like what disk they're doing them to, how much data they're transacting, and the process ID associated with the process that's doing this disk IO. So it works like top, but instead of showing you the top most expensive processes on your system, it's showing you the top running block IO requests on your system. And this is kind of zooming out away from the individual process introspection, and instead looking kind of more system wide, but it's giving you specific application data. So if you then were like, hey, why is K worker D doing all this IO? Then you use your tool like Strace to connect to K worker D to figure out what K worker D is doing, or not D, K worker. Or you saw a couple of Python things. So you would use your Strace to attach the process ID of the Python thing to then, look closer at what that Python thing is doing. All right, I mentioned there are a couple other tops there. So I'm just going to look at user share BCC Tools star top. So I also like TCPTOP. All right, so TCPTOP is showing you the top TCP connections running on your machine. And then the process ID, what command is associated with it, the local address and the remote address, and then the RX and TX is the transferred and received kilobytes. So you can kind of see all the open TCP connections that are on your machine and what they're doing. And again, if there's one of these that's kind of interesting, well, there's the process ID that you have. So you would then use Strace to connect to that process ID to figure out what it's actually doing during that process ID. All right, with BioTop or any other IO tracing tool, how do you trace it back to the actual disk? Well, with BioTop, it actually tells you the disk, right? So let me go back to BioTop. So as we're doing the request under this disk field, that's going to tell you the disk that the block IO request was made to. So that's how you trace it back to the actual disk. If you're instead asking like files, let's see here. There is a file top, but I think it requires some additional options. So let's try it. It's probably going to complain to me. Let's see. Oh, there we go. So this tells you the reads and writes, the read kilobits and write kilobits, and then the actual file that's being used by the process ID at the front of each line. So block IO top is giving you kind of general across all your block devices, and this is giving you specific files. But here, notice there's not any information on what block device this file belongs to, right? So, looking at xterm 256 color, just in the top, I can't see what that lives on. So I could do something like a find for xterm 256 color. Xterm 256 color. And so this is user share term info. User is not its own separate file system, so it's going to be part of slash here, and it's actually transacting on dev VDA3. So that's kind of how you figure out what goes where and what's being used by what. All right. Yeah, so that's the stuff I wanted to tell you about for kind of general system profiling with the BCC tools. But I did want to show you a couple other tools, or at least mention a couple other tools as well. All right, so we're using Strace to do system calls, or Ltrace to look at shared object library calls. And this is handy for doing things like figuring out what an application is doing. But in BCC Tools, you actually have other cooler options. Specifically, Java calls. So you could use Java calls to wrap a Java application, and it gives you the same kind of information as an strace, but it's actually showing you the Java application calls that are being made during the running of this Java application. There's also ones for Perl and Python and Ruby and PHP. So you can do profiling of your language-specific runtime applications, and it'll give you more specificity on what that language runtime application is doing. So if you want to see what Python calls are being made by your Python application, use Python calls, and it'll show you all the Python libraries and Python calls that are being made from within your application. So this is really handy if you, again, are an application developer working with this language. It may be interesting if you are an administrator running someone else's application, but you're going to have some familiarity with this language runtime. So for example, like I don't know much about Ruby. So if I looked at the output of a Ruby calls, it's probably not going to mean a whole lot to me. But maybe if I know who wrote the Ruby application, I can provide that information to them, and we can talk about what it's doing and what we're seeing on the system, so that they can kind of see a snapshot of what's happening during their Ruby application, and they can then look at their Ruby application and be like, oh yeah, this is what's doing. Oh, all right, I see what's happening here. And that's what's causing some system behavior that I'm describing as a problem, right? So these things, if you're not the actual application developer, can still be pretty useful if you know who the application developer is, to be able to have that conversation with them about what the system operation looks like, and what's, after you've done these traces, here's the trace data for what their application is doing. So I've always had some really good conversations with developers if I can come in with data about their application, so that, because they're more familiar with what they're trying to do in their application, to better explain why it's behaving a certain way. All right. Cool. So I don't think there's any more questions. Next time on Into the Terminal, we're going to be doing some more shell stuff. I think it's sed and awk and something else. It was a viewer request on a comment. So that's what we're going to be doing next time on Into the Terminal. Hopefully Nate will be feeling better, so he will join us. And then the other thing is, I saw a request earlier for IDM and maybe Active Directory. There have been a couple of videos produced by our support staff on LDAP and Active Directory recently. So check the recent videos in the channel, and there might be a couple of things that you're interested in there. We have been talking about doing a mini series on Identity Manager for a while. I think Nate and I first talked about it like last spring, like a year ago. But it's a function of like breaking off enough time to actually produce it. So it's in the backlog, and we'll see about maybe breaking off some time after Red Hat Summit to produce it this year. Yeah, I think that's it. So thanks for watching. If you are a deferred viewer and have questions, please leave us a comment. Nate and I do read and respond to comments. And until next time, enjoy Into the Terminal.